All right, this is the Math 215 Lab 8 tutorial, and this one is pretty easy. There isn't much to it, and so I'll just go over them each really quickly. For problem 1, kind of starts off with learning how to do a linear transformation with a matrix. And so the transformation that we're given is this. We're given the transformation matrix as A up above. And what we want to do is that when we take in some vector x, we want to return the transformation based on this matrix. Now the nice thing that we can do is that our t of x is defined always to be A, which is our transformation matrix, times that x. And so all you need to do for this function is just multiply A and x, which you can do with the np.matmul function. You'll be using this function a lot for this lab. So that's problem 1. Problem 2 is similar, but playing on this idea for different ones that we're given. So if we start off with stretch, we're given some vector x. We're calling it image in this, or it's a matrix x. We're calling it image in this scenario, and we want to times it by these different transformation matrices. So for stretch, for instance, our matrix C is going to be, that's not, A0, 0B. And so what we need to do for each of these functions, and not just talking about stretch, but also shear, reflection, and rotate, is that we want to first set up our matrix. I would call it something like A equals. So for this one, it would be something along the lines of A equals np.array of, because this is a matrix, you want to have two sets of brackets. This one will be A, comma 0, and then you'll want to add another row to do 0, comma B, and then end with two brackets as well. And so that will be how you set up your stretch one. I won't show you exactly how to do the rest of the ones, but it will be something very, very similar to this. And so then you'll multiply your A times your X, or your image in this instance, just like you did in problem 1, to return your new transformed matrix. And so yeah, that should cover all the ones in problem 2. Problem 3 is by far the hardest on the slab, and the advice that I would give is to do them sequentially. So the first one, we want to stretch the image vertically by a factor of 2. And the way that I would do this when constructing our transformation matrix itself, the nice thing is if A is our transformation matrix, then A times the identity will still be A. That's just the law of the identity matrix. And so if we treat our X matrix, or image in this case, as I, where that equals I, then that's still going to equal A. So if we want to figure out the transformation matrix for stretch in this instance, we can do stretch, and then rather than saying a certain image or a certain X, we'll just use identity. And that's how we can start off and just get our transformation matrix, even though we're kind of multiplying two together at the same time. And then for this one, yeah, we want to stretch the image vertically by a factor of 2, so X will stay the same, and Y will grow by 2. Now to do this again and again with each other, what I would do is say, because say we have here, we have our matrix A, and we know that we want to multiply that transformation matrix by B, like this. But that's kind of the same way that we did here. So we did B of A almost. So that's how I would go and do the next steps. Is the next step, I'm pretty sure, is rotate. Yeah, so we'd want to do rotate of stretch identity, and then we would include our other ones. And remember, you're rotating clockwise, so you actually go negative however many radians you need to have. So that's how I would set it up. And then a couple of notes, yeah, just do it negative for clockwise. And then when they specify reflect, the way they want you to do it is have your image, whatever that may be, and then they want you to put it as 2, -3. Your y's will always go here, and your x will always go here. So you can write that also as 1, -3 halves, or 2, -3, whichever you prefer. But that's how you would write that line, because that just seems to trip people up every now and then. And then the horizontal, yeah, you'll shrink x by, or your stretch x by 1/2 and keep y the same. And so that should help on problem 3. Again, that's probably the hardest one. And so once you have all that written out, you can move on to problem 4. And problem 4 is also kind of tough. And so we're given some matrix A, just 2 by 2, that has A, B, C, and D. Now, we want to figure out, so if you go back and you see on the previous page, they say E1 equals 1, 0, and E2 is 0, 1. And just to explain these again, these are our elementary vectors that define our unit square in this instance, with E1 being that way and E2 being that way. And so I like to think that when we multiply E1 by A, our transformation matrix, let's see, we'll get A times 1 plus B times 0, and then we'll get C times 1 plus D times 0, or A and C. And so we can see that our altered first E1, or in this case I think they call it V, is going to be the first column. And so I'll draw that right here. And our second column will be our W, because that's the transformed second vector. And the way to get the cosine, or the sine in this instance, because if you notice in the diagram, the area of our parallelogram is going to be A times B times sine theta. And the way to get that sine theta, unfortunately all we're given is our cosine theta. And you can do cosine theta with doing the dot product and the np.lnog.norm like they mention. But that only gives us cosine theta. Now the way I would turn that into theta is, doing this arc cosine. And so that will give us just theta. And then by doing the sine of the arc cosine, we can get the sine of theta. And so you'll replace that cosine of theta with the whole v dot w over the magnitude of v and the magnitude of w. And then your a and b are just going to be your v and w respectively. So that's problem 4. And hopefully that works out well. That's the second hardest problem for sure. And then problem 5 you can do by hand, and you should have reviewed enough of that in 213 to be able to do that. And then the last one, because I think problem 7 you can also do by hand. Problem 6, you want to figure out the area of this ellipse matrix. And so I'll go back to the equation on the previous page, which is the area of E equals the absolute value, be sure to include the absolute value, of the determinant of A times the area of C. Now the area of C, really quickly, will just be the area of a unit circle, meaning a circle with a radius of 1. So that will just be pi r squared, where r is 1. So your area will just be pi. As for the determinant of A, kind of following a similar principle to what we did in the last problem, where our altered E1 and E2, in this case called V and W, are given to us. But if you remember, if our altered matrix is going to be V and W, or in this case 1.5, 0.5, and 1 and negative 2.75, that's going to be times our E1 and E2, which is this, with this being our transformation matrix. Now you can solve this for A through some other linear algebra, or you could just notice that this is the identity matrix, and anything times the identity matrix will equal itself. And so your A matrix will be this matrix, where this is your V and your W. And so you can just figure out the determinant by doing those two minus those two. And so that will give you a determinant. You times that by pi, which is the area of C, and you should get the area of E. And remember to do the absolute value on that determinant, because you should get a negative value if you don't. And then, that will wrap up problem 6. And then problem 7, I would just recommend doing them like with a calculator or by hand. So that's lab 8. I hope you guys don't find too much trouble with it. Just those couple of tricky problems that might get you caught up. All right, have a nice week.